The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
We'll get started. So today we are going to dive into some parallel architectures. So the way, if you look at the big world, is there's discovering parallelism. You can do it implicitly, either by hardware or the compiler. So the user won't see it. It will be done behind user's back, but can be done hardware compiler, or explicitly visible to the user. So the hardware part is done in superscalar plus process, and all those things will have explicitly parallel architecture. So what I'm going to do is spend some time just talking about implicitly parallel superscalar process, because probably the time you guys were born till now, this was being the mainstream, and people are building these things, and we are used to it. And now we are kind of doing a switch, and then we'll go into explicitly parallel process and kind of look at different types in there and get a feel for the big picture in there. So let's start with implicitly parallel superscalar process. So there are two types of superscalar process. One is what we call statically scheduled. Those are kind of simpler ones, where you use compiler techniques to figure out where the parallelism is. And what happens is the computer keep executing, instead of one instruction at a time, the few instructions next to each other in one bunch, like a bundle after bundle type thing. On the other hand, dynamically scheduled process, things like the current Pentiums, are a lot more complicated. They have to extract instruction level parallelism. IAP doesn't mean integer linear programming, it's instruction level parallelism. Schedule them as soon as operands becomes available. When the data is available, you run these instructions. Then there's a bunch of things to get more parallelism, things like rename register to eliminate some dependencies. You execute things out of order. If things, later instructions, the operands become available early, you'll get those things done instead of waiting. You can speculate to execute. I'll go through a little bit in detail to kind of explain what these things might be. Why is this not going down? Oops. So if you look at a normal pipeline, so this is a 004 type pipeline. So what I have is this a very simplistic, like 4-stage pipeline in there. So a normal microprocessor, single issue will do something like this. Okay, and if you look at it, there's still a little bit of parallelism here, because you don't wait till the first thing finishes to go the next thing. If you look at superscalar, you have something like this. This is an in-order superscalar. What happens is every cycle, you, instead of doing one, you fetch two, you decode two, you execute two, and so on and so forth. In out-of-order superscalar, these are not going in this very nice boundaries. You have a fetch unit that fetch like hundreds ahead, and it keep issuing as soon as things are fetched and decoded to the execute unit, and it's a lot more of a complex picture in there. So I'm not going to show too much of a picture there, because it's a very complicated thing. So the first thing a process has to do is it has to look for true data dependencies. True data dependence says that this instruction in fact is using something produced by the previous guy. Okay, so this is important because if the instructions are data dependent, they cannot be executed simultaneously, because you have to wait till the first guy finishes to get the second guy. Cannot be completely overlapped, and you can't execute them in out of order, because you have to make sure the data comes in before you actually use it. And in computer architecture jargon, this is called a pipeline hazard, and this is called a read after write hazard, or row hazard. What that means is you have to you do the read, that the write has to finish before you can do the read. And in a microprocessor, people try very hard to minimize that time you have to wait to do that, and you really have to honor that. So what in hardware software we have to do is you have to preserve this program ordering. The program has to be executed sequentially, determined by the source program. So source program says some order of doing things. You better, if there's some reason for doing that, you better actually adhere to that order. You can't go and just do things in a haphazard way. And dependencies are basically fact of the program. So what you got, I mean, if you're lucky, you'll get a program without too many dependencies, but most probably you'll get programs that have a lot of dependencies. That's normal. So there are a lot of importance of their dependence because it indicates possibility of these hazards, how this dependencies has to work. And it determines the order which the results might be calculated, because if you need one to do the next result of that to the next, you have what you call a dependence chain, and you have to execute that in that order. And because of dependence chain, it sets the upper bound of how much parallelism that can be possibly expected. If you can say all your program, there's nothing dependence, every instruction just can go anytime, and then you can say the best computer will get done in one cycle, because everything can run. But if you say the next instruction depends on the previous one, next instruction depends on the previous one, you have a chain, and no matter how good the hardware, you have to wait till that chain finishes, and you don't get that much parallelism. So goal is to exploit parallelism by preserving the program order where it affects the outcome of the program. So we want to have a look and feel like the program is run on a nice single issue machine that do one instruction after another after another. That's the world we are looking in, and then we are doing all this underneath to kind of get performance but give that abstraction. So there are other dependencies that we can do better. There are two types of name dependencies. That means there's no real program use of data, but there are limited resources in the program, and you have resource contentions. So the two types of resources are registers and memory. And so when you have resource contentions, so the first name dependence is what we call anti-dependence. Anti-dependence means that I am going to what I need to do is I want to write this register, but the previous instruction I am actually reading the register. I'm not really reading because I'm writing the next one. I'm not using the value, but I cannot write it until I have read that value, because the minute I write it, I lose the previous value, and if I haven't used it, I am out of luck. So there might be a case that I have a register that I'm reading the register and writing with some new value, but I have to wait till the reading is done before I do this new write. And that's called anti-dependence. So what that means is we have to wait to run this instruction until this is over. You can't do it before that. So this is called a write after read hazard in the architecture jargon. The other dependence is what you call output dependence. Two guys are writing the register, and then I'm reading it. So I want to read the value the last guy wrote. Okay, so if I reorder that, I get a wrong value. Actually, you can even do better in here. How can you do better in here? Yeah, you can eliminate the first one because nobody's using that value. So that's you can go in further and further. But this is also hazard. This is called write after write hazard. And the interesting thing is, by doing what you call register renaming, you can eliminate these things. So why do both has to use the same register? In these two, if I use a different register, I don't have that dependency. And so a lot of times in software and also in modern superscalar hardware, there's this huge amount of hardware resources that actually do register renaming. So they realize there's anti-dependence, output dependence. Say, wait a minute, why do I really have to do that? I can use a different register. So even though you have Intel basic x86 says we only have 8 registers, there are about 100 registers behind, hardware registers. This basically let you do this reordering and renaming, register renaming. So the other type of dependence is control dependence. So what that means is, if you have a program like this, you have to preserve the program ordering, and what that means is S1 is control dependent on P1, because depending on what P1 is, it will depend whether S1 gets executed. S2 is control dependent on P2, but not P1. So it doesn't matter what P1 does, S2 will execute only if P2 is true. So there's a control dependency in there. So another interesting thing is control dependence you don't need to preserve it all the time. You might be able to do things out of this order. Basically what you can do is, if you are willing to do more work, you can say, wait, I'll do this. I don't know whether I really need it because I don't know whether P2 is true or not, but I'll just keep doing it. And then if I really want it, I actually have the result ready for me. And that's called out of order, it's called speculative execution, sorry. So you can do speculation. So you speculately think that you will need something and go do it. So speculation provides you with a lot of increased IAP because it can overcome control dependence by executing through branches before even you know where the branch is going. And a lot of times you can go through both directions. Say, wait a minute, I don't know which way I'm going. I'll do both sides. And I know at least one side you're going, and that will be useful. And you can do going more and more. And as soon as you realize you're doing so much more work than actually really useful. So the first level of speculation is speculation basically says you go, you do fetch, issue, execute everything. You do the end of the thing without just committing. You wait until the commit to make sure that the right thing actually happened. So this is the full speculation. There's a little bit of less speculation called dynamic scheduling. If you look at a microprocessor, one of the biggest problems, the pipeline stall is a branch. Because you can't keep even a pipeline going, even in a single issue machine if there's a branch, because the branch congestion gets resolved a lot after the next instruction has to get fetched. So if you do a normal thing, you just have to really stall the pipeline. So what dynamic scheduling or a branch predictor sometimes do is, it will say, I will predict where the branch is going. So I might not fetch both directions, but I will speculatively go fetch down one path because it looks like which is going. For many times, like for example in a loop, 99% of the time you are going in the back edge because you don't go through that. And if you predict that, you are mostly correct. So the branch predictors are pretty good at finding these kind of cases. There are very few branches that are kind of 50-50. Most branches has a preferred path. And if you find the preferred path, you can go through that and you don't pay any penalty. The penalty is if you made a mistake, you have to kind of back up a few times. So you can at least do in one direction. That's most hardware do it. Even the simplest things do that. But if you do good speculation, you go both. You say, there's a chance if I go the other path, I'm going to lose a lot. So I'll do that too. So that do a lot of expensive stuff. And basically this is more for data flow model. So as soon as data get available, you don't think too much about control. You keep firing that. So today's superscalar processors has huge amount of speculation. You speculate on everything. Branch prediction, you assume all the branches multi-level down, you predict go there. Value prediction, you look at value and say, hey, I think it's going to be 2. And in fact, there's a paper that says there's about 80% of program values are 0. Okay? And you say, okay, I'll think it's 0 and I'll go on. And if it is not 0, I'll have to come back and do that. So things like that. Okay?
Do you know what percentage of the time that has to go back?
I guess if a lot of times I think it is probably 80-20 type thing, but 20. But if you do too much, you're always backing up. But you can at least do few things down, assuming it's 0. So things like that. I mean, people try to take advantage of statistical nature of programs, and you're mining every day. So basically, there's no like it's almost at the entropy. So every information is kind of taken advantage in the program. But what that means is you're wasting a lot of time cycles. So the conventional wisdom was you have Moore's law. You keep getting these transistors. There's nothing to do with it. So let me do more other work. We'll predicate. We'll do additional work. We'll go through multiple branches. We'll assume things are 0 because what's wasted? Because it's extra work. If it is wrong, we'll just give it up. Okay, so that's the way it went, and thing is, it's very inefficient. Because a lot of times you are doing, think about even a simple cache. If you have 4-way cache, every cycle when you're doing a memory fetch, you're fetching on all 4, assuming one of it will have hit. Even if you have a cache hit, only one bank is hit. All other 3 banks are not hit. So you're just doing a lot more extra work just to get to one thing. Of course, because if you wait till figure out which bank, it's going to add a little bit more delay. So you won't do it parallel. You know that it's going to be one of the lines. You just go fetch everything, and then later decide which one you want. So things like that really waste energy. And what has been happening in last 10 years is you double the amount of transistors, and you add 5% more performance gain. because there's statistically you have mined most of the low-hanging fruit. There's nothing much left. So you're getting to a point that has a little bit of a statistical significance, and you go after that. So of course, most of the time it's wrong. And so this leads to this chart that actually yesterday also point out. So we are going from hot plate to nuclear reactor to rocket nozzle, and kind of like that is the, if we continue going in that direction, that is the path, because we are just doing all this wasteful thing. And right now the power consumption on processors are significant enough in both things like laptop, where you, because the battery is not getting faster, as well as things like Google. So this doing this extra just useless work is actually starting to impact. So for example, if you look at something like Pentium, you have a 11 stage of instructions. You can execute 3 x86 instructions per cycle. So you are doing this huge superscalar thing, but something that had been creeping in lately is also some amount of explicit parallelism. So they introduce things like MMX XSC instructions. They are explicit parallelism visible to the user. So it's not hiding, trying to get parallelism. So we have been slowly moving to this kind of model saying, okay, yeah, if you want performance, you actually do something manual. So people who really cared about performance had to deal with that. And of course, we put multiple chips together to build a multiprocessor. It's not in a single chip that actually do parallel processing. So for about 3-4 years, if you buy a workstation, it had 2 processors sitting in there. So dual processor, quad processor machines came about, and people start using that. So it's not like we are doing this shift abruptly. We have been going to that direction for people who really cared about performance actually had to deal with that and were actually using that. Okay, so let's switch gears a little bit into explicit parallelism. So this is kind of where we are today, where we are switching. So basically, these are the machines that parallelism exposed to software, either compiler. So you might not see it as a user, but it's exposed to some layer of software. And there are many different forms of it. So from a very loosely coupled multiprocessor sitting on a board, or even sitting on multiple machines, things like a cluster of workstations, to very tightly coupled machines. So we will go through, figure out what are all the flavors of this is. Mm-hmm.
So is the main difference between the level of parallelism the compiler can exploit and the processor can exploit the fact that the compiler knows the higher level instruction? Is that the main difference, or is it?
It goes both ways. So what processor knows is it knows values for everything. So it has full exact knowledge of what's going on. Compiler is in abstraction. In that sense, processor wins in those cases. On the other hand, compile time doesn't affect the runtime. So compiler has a much bigger view of the world. And it can do, because even the most aggressive process can't look ahead more than 100 instructions. On the other hand, compiler sees ahead of millions of instructions. And so compiler has the ability to kind of get the big picture and do things, global kind of things. But on the other hand, it loses out when it doesn't have information. Whereas when you do the hardware parallelism, you have full information.
You don't have to give up one at the cost of the other.
I mean, the thing is, I don't think we have a good way of combining both very well. Because the thing is, sometimes global optimization needs local information, and that's not available to runtime, and global optimization is very costly, so you can't say, okay, I'm going to do it anytime. So I think it's kind of even hybrid things. There's no nice mesh in there. So if you think a little bit about parallelism, what interesting thing is this Little's law. Little's law say parallelism basically parallelism is a multiplication of throughput versus latency. Okay, so the way to think about that is the parallelism is dictated by the program in some sense. Program has a certain amount of parallelism. Okay, so if you have a thing that has a lot of latency to get to the result, okay, what that means is there's a certain amount of throughput you can satisfy. Okay, so whereas if you have a thing that a very low latency operation, you can go much wider. Okay, so if you look at Intel process, what they have done is the superscalers, they have actually, to get things faster, they have a very long latency because they know they couldn't go more than 304 wide. So they went like 55 depth pipeline, 3 wide. Because you can go fast, but so they assume the parallelism fits here. So still you need a lot of parallelism. Even so you say 3 wide issue machine. So you say, yeah, it's 3, it's no big deal. But no, if you have 55 depth pipeline, you need to have 165 parallel instructions on the fly in given time. So that's the thing. Even in a modern machine, there's about hundreds of instructions on the fly because the pipeline depth is so large. So even so, if you say 3 issue, it's not that. I mean, this happens in there. So this gives designers a lot of flexibility in where you are expanding. And in some ways, you can have a lot. There are some machines that are a lot wider, but the latency is, for example, if you look at a Itanium, its clock cycle is about half the type of the Pentium because it has a lot less latency, but a lot wider. So you can do these kind of trade-offs. So types of parallelism. So there are 4 categorizations here. So one categorization is you have pipeline. You do the same thing in a pipeline fashion. So you do the same instruction, you do a little bit, and you start another copy of another copy of another copy. So you kind of pipeline the same thing down here. Kind of a vector machine. We'll go through categories, kind of fit in here. Another category is data level parallelism. What that means is, in a given cycle, you do the same thing, same instruction for many things in here. And then next cycle you do something different, stuff like that. A thread level parallelism breaks in the other way. Thread level parallelism says, okay, I am not connecting the cycles, they are independent. Each thread can go do something different. Okay, and instruction level parallelism is kind of a combination because what you're doing is you're doing cycle by cycle, they are connected, and each cycle you do some kind of combination of operations. So if you look at this closely, so pipelining hits here, data parallel execution, things like SIMD execution hits here, thread level parallelism, instruction level parallelism. So different models of parallelism, what software people see, kind of fits also in this architecture picture. So when you're designing a parallel machine, what do you have to worry about? First thing is communication. I mean, that's the big problem in here. How do parallel operations communicate the data results? Because it's not only issue of bandwidth, it's about the issue of latency. Because the thing about bandwidth is that had been increasing by Moore's law. Latency is speed of light. So as I point out, there's no Moore's law on speed of light, and you have to deal with that. Synchronization. So when people do different things, how do you synchronize at some point? Because you can't keep going on different paths. At some point, you have to come together. What's the cost? What are the process of going in? Some stuff it's very explicit, very almost you have to deal with that. Some machines it's built in. So every cycle you are synchronizing. So that adds. Sometimes it make it easier for you. Sometimes it make it more inefficient. So you have to figure out what is in here. Resource management. Thing about parallelism is you have a lot of things going on. And managing that is a very important issue. Because sometimes if you put things in the wrong place, the cost of moving, cost of doing that might be much higher. That really reduce the benefit of doing that. And finally, the scalability. How do you build processes that not only can do 2x parallelism, but can do 1,000? How can you keep growing with Moore's law? So this is so there are some ways you can get really good numbers, small numbers, but as you go bigger and bigger, you can't scale. So here's a classic classification of parallel machine. This has been developed by Mike Flynn in '66. So he came up with 4 ways of classifying machines. First, he looked at how instruction and data is issued. So one thing is single instruction, single data. So there's a single instruction given each cycle, and it affects single data. This is your conventional uniprocessor. Then he came up with a SIMD machine, single instruction, multiple data. So what that means is a given instruction affects multiple data in here. So things like there are two types, distributed memory and shared memory. I will go to this distinction later. So there are a bunch of machines. So for a good old time, this was a useful trick because sequence or what run the instructions was a pretty substantial piece of hardware. So you want to build one of them and use it for many, many data. And even today in a Pentium, if you are doing a SIMD instruction, you just issue one instruction, it affects multiple data, and you can get a nice reuse of instruction decoding, reduce the instruction bandwidth by doing SIMD. Then you go to MIMD, which is multiple instruction, multiple data. So we have multiple instruction streams, each affecting some its own data. Okay, so each you have data streams, instruction streams separately. So things like message passing machines, coherent and non-coherent shared memory. I'll go into details, this coherence and non-coherence later. So there are multiple categories within that too. And then finally, there's kind of a misnomer, MISD. There haven't been a single machine. It doesn't make sense to have multiple instructions work on single data. So this classification, right now, question? Multiple instructions, single data. I don't know. I mean, I mean, you can try to fit something there just to have something, but I don't think it doesn't fit really well into this kind of thinking. So I don't like that thinking. So I was thinking, how should I do? So I came up with a new way of classifying. So my classification is, what's the last thing you are sharing? Because when you are running something, if it is some single machine, something has to be shared, and some things have to be separate. So are you sharing instructions? Are you sharing the sequencer? Are you sharing the memory? Are you sharing the network? So this kind of fits many things nicely into this model. So let's go through this model and see different things in here. So let's look at shared instruction process. So there had been a lot of work in good old days. I mean, did anybody know Goody actually made supercomputers? So not only they made tires, for a long time they were actually making process. To GE make process, stuff like that. And so long time ago, this was a very interesting proposition because there was huge amount of hardware has to be dedicated to doing the sequence, running the instruction. So just to share that was a really interesting concept. So people build machines that basically a single instruction stream affecting multiple data in there. I think very well-known machines are things like thinking machines, CM1, MASPA MP1, which had 16,000 processors, small processors, 4-bit processors. You can only do 4-bit computation. And then you can do, every cycle you can do 16,000 of them, 4-bit things in here. It really fits into the kind of things they could build in hardware those days. And you had one control in there. So it's a neat thing because you can do a lot of work if you actually can match it in that form. So the way you look at that is to run this array, you have this array controller. And then you have processing elements, huge amount of them. And you have each processing element mainly had distributed memory. Each has its own memory. And so given instruction, everybody did the same thing to memory or arithmetic in there. And then you had also interconnect network. So you can actually send data. In a lot of these things have a near neighbor communication. You can say you can send data to your near neighbor. So everybody kind of shift either 2D or some kind of torus kind of mapping in there. And you can actually get really good, if you can program that, you can get really good performances there. And each cycle, it's very synchronous. So each cycle, everybody do the same thing, go to the next thing, do the same thing. So the next very interesting machine is this Cray-1. I think this is one of the first successful supercomputers out there. So here's the Cray-1. It is this kind of round seat type thing sitting in here. Everybody know what was under the seat? Cooling. So here's a photo. I don't think you can see it. You can probably look at it when I put this on the web. Was this entire cooling mechanism. In fact, Seymour Cray at one time said one of his most important innovations in this machine is how to cool the thing. And this is generation, again, the power was a big thing. And so each of these columns had this huge amount of boards going, and in the middle had all the wiring going. So you had this huge mess of wiring in the middle, that interconnect that thing. And then you had all these boards in there in each of these. So this is the Cray 1 processor.
Do you know your laptop is way faster than that crazy?
Yeah. So what did we have the clock speed in here?
I'm guessing. Yeah, it was under 80 megahertz.
80 megahertz. Yeah. Okay.
Yeah.
So yeah, yeah. So and that cost like whatever, like $10 million or something like that at that time. Yeah. So I mean Moore's law. It's just amazing. I mean, if you apply Moore's law to any other thing we have, you can't like do the comparison. So we are very fortunate to be part of that generation. Yeah. So what it had this 3 types of registers. It had scalar registers, address registers, and vector registers. The key thing there is the vector register. So if you want to do things fast, fastness of the word, so you can do a lot of computation in a short amount of time by using the vector registers. So the way to look at that is, normally when you go to the execute state, you do one thing. In a vector register, what happens is it got pipeline. So execute stage happen one word, next. You can do up to 64 or even bigger. I think it was 64 length 64 things. So you can, so that instruction, so you do few of these, and then this stage keep going on and for 64. And then you can pipeline in a way that you can start another one. Actually, this will use same execution rate. So you have to wait till that finish to start. So what happens is so you can pipeline to get huge amount of things going through the pipeline, and so each cycle you can graduate many things going on. So.
I'm trying to get straight into my own head. My notion, but I'm not sure if I'm right, that's what I'm asking you, is machines like the Cray, and then when you were talking about some of the vector operations you could do on the Pentium and even on the cell processor, those were by and large a relatively small set of operations, like dot products and vector times scalar. While on the other hand, like when you look at the SIMD machines, they had a much richer set of operations. Is that right?
I think with scatter gather and things like conditional execution, I think vector machines could do a fair large. I mean, it's painful.
That is a little bit set, right?
The SIMD instruction in Pentium. Yeah, I think that is mainly targeting signal processing type stuff. It didn't have they don't have they don't have real scatter gather.
And the cell processor?
Cell is distributed memory. So.
No, but on one of the what do they call them?
I don't think it has scatter gather either. It's just basically you have to do exactly align words in, word out. So yeah, I mean IBM is always about doing align. So in even Altivec, you can't even do unaligned access. You have to do aligned access. So even if the data is not unaligned, you have to pay a big penalty in there. So yeah. So if you look at how this happens, so you have this entire pipeline thing. So when things get started, the first value is at this point done in one clock cycle. Next value is halfway through the adder. Another value is in some part of the, so adder is also pipeline, the ALU is pipeline. And other values are kind of feeding nicely into that. So if you have this is called one lane. You can have multiple lanes. And then what you can do is each cycle you can get 4 results out. And the next ones are in the middle of that, next ones are in the middle. So what you have is a very well pipelined machine, so you can kind of pipeline things in there. So you can have either one lane or multiple lanes pipeline coming out. So if you look at the architecture, what you had is you had some kind of vector registers feeding into these kind of functional units. And so at a given time, you can, in this one, you might be able to get 8 results out because everything gets pipeline. But the same thing is happening in there. So clear how vector machine works. So it's not really parallelism. It's basically, especially if you have one, it's a super pipeline thing. But given one instruction, it will crank out many things for that instruction. And doing parallelism is easy in here too, because it's the same thing happening to very regular data sets. So there's no notion about synchronizations and all these weird things. It's just a very simple pattern. So the next thing is the shared sequencer processor. So here, it's similar to the vector machines because each cycle you issue a single instruction. But the instruction is a wide instruction. It had multiple operations in the same instruction. So what it says is, okay, I have multiple execution units, I have memory units, separate units, and each instruction I will tell each unit what to do. Okay, and so something you might have 2 integer units, 2 memory load store units, 2 floating point units. Each cycle you tell each of them what to do. So you just kind of keep issuing instruction that affects many of them. So sometimes what happens is if this has latency of 4, you might have to wait till this done to go the next instruction. So if one guy takes long, everybody has to kind of wait till that. So it's very synchronous going. So things like synchronization stuff was not an issue in here. So if you look at a pipeline, this is what happens. So you have this instruction. It's instruction fetch. You are fetching a wide instruction. You're not fetching a simple instruction. You decode the entire thing, but you can decode it separately, and then you go execute on each execution unit. One interesting problem here was this was not really scalable. What happened here is each functional unit, if you had one single register file, has to access the register file. So each function unit say I am using register R1, I am using R3, I am using R5. So what has to happen is a register file has to have basically if you have 8 functional units, 16 outputs and 8 inputs coming in. And then of course when you build register file, it has a scale, so it had like huge scalability issues. So it's a quadratically scalable register file. Question?
Sequencer, your shared sequencer, is that the instruction fetch and the decoder?
Yeah. So I mean even executes also it's basically you have to wait till everybody is done. There's nothing going out of any order. And memory also, since everybody is going to memory, this was not scalable. So people try to build, you can do 4, 8 wide, but beyond that, this register unit and memory interconnect became a big mess to build. And so one kind of modification thing people did was called clustered VLIW. So what happens is you have very wide instruction in here. It goes to not one cluster, different clusters. Each cluster has its own register file, its own kind of memory interconnect going on there. And what that means is if you want to do inter-cluster communication, you have to go through a very special communication network. So you don't have this bandwidth expansion register. So you only have, we'll say, 2 execution units. So you only have to have 4 in and 4 out and 1 in to the register file in cycle. And then if you want more other communication, you have a much lower bandwidth interconnect that you'd have to go through that. So what this means is you kind of exposed more complexity to the compiler and software. And the rationale here is most programs have locality. It's not like everybody always want to communicate with everybody else. So there are some locality in here. So you can basically cluster things that are local together and put it in here. And then when other things have to be communicated, you can use this communication and go about doing that. So this is kind of the state of the art in this technology. And something like what I didn't put, the Itanium kind of fits in here, Itanium processor. So then we go to shared network. There have been a lot of work in here. People have been building multiprocessors for a long time because this is a very easy thing to build. So what you do is, if you look at it, you have a processor unit that connects its own memory. And it's like a multiple workstation. Then it has a very tightly connected a network interface that go to interconnect network. So you can even think about a workstation farm as this type of a machine. But of course, the network is a pretty slow one that requires Ethernet connector. But people build things that has a much faster networks in there. And this was designed in a way you can build hundreds and thousands of these things, nodes in here. So today, if you look at the top 500 supercomputers, bunch of them fits into this category because it's very easy to scale and build very large things. And
Are you putting SMPs in this list or some other place?
SMPs is mostly shared memory. So it's this shared network. I will do shared memory next in some. So but there are problems with it. So all the data layout has to be handled by software or by the programmer basically. if you want something outside in your memory, you have to do very explicit communication. Not only you, the other guy who has the data actually has to cooperate to send it to you, and he needs to know that now you have the data, and all that management is your problem. And that makes programming them, these kind of things, very difficult, which you'll probably figure out by the time you are done with Cell. So Cell has a lot of these issues too. And the problem here is not dealing with most of the data, but the kind of corner cases that you don't know about that much. There's no nice safety net saying, I don't know who's going to access it. I'll let the hardware take care of. There's no hardware. You have to take care of yourself. And also, message passing has a very high overhead, because most of the time, in order to do message, you have to invoke some kind of a kernel thing. You have to actually do a kernel switch that will call the network. It's operating system involved process basically to get a message in there. And also when you get a message out, you have to do some kind of interrupt or polling, and there's a bunch of copies out of kernel. And this became pretty expensive proposition. So you can't send messages size of one instruction. So you have to accumulate a huge amount of things to send out to amortize the cost of doing that. You can send message. Sending can be somewhat cheap, but receiving is a lot more expensive, because receiving you have to multiplex. You have no idea who it's coming to. So you have to receive, you have to figure out who is supposed to get. Especially if you are running multiple applications, it might be for some other application. You have to context switch. So it's a big mess. That is where people went to shared memory process, because it became easier message to use. So basically, that is the SMPs Alan was talking about. Nice thing, it will work with any data placement. It might work very slowly, but at least it will work. So it makes it very easy to take your existing application and first getting it working, because it will just work in there. You can choose to optimize only critical sections, and you can say, okay, this section, I know it's very important. I will do the right thing. I will place it properly, everything. And the rest of it, I can just leave alone, and it will go get the data and do it right. Even it will run sequentially, of course. But at least the memory part, I don't have to deal with it. If some other memory just once in a while access that data that you have actually parallelized, it will actually work. So you only have to worry about the regions that you are parallelizing. And you can communicate using load store instructions. You don't have to get OS involved to do that. And it's a lot lower overhead. So instead of 5 to 10 cycles, instead of hundreds to 1,000 cycles to do that. And most of these machines actually supplied some instructions to do this communication very fast. There's a thing called fetch and op, thing called load, link, store conditional operations. There are these very special operations where if you are waiting for somebody else, you can do it very fast. So if two people are communicating, so people came up with these very fast operations that low cost, as well as if the data is available, it will happen very fast, synchronization. And when you start to build large systems, you can actually give a logically shared view of memory, but underlying hardware can be still distributed memory. So there's a thing called, I will get into when you do synchronization, directory-based cache coherence. So you give a nice, simple view of memory, but of course, memory is really distributed. So that actually kind of gives best of both worlds. So you can keep scaling, build large machines, but the view is a very simple view of machine. And so there are two categories in here. One is non-cache coherent and then hardware cache coherence. So non-cache coherence kind of give a view of memory as a single address space. But you have to deal with that. If you write something to get the value to me, you have to explicitly say, okay, now send it to that person, but we still in the single address space. It doesn't give the full benefits of a shared memory machine. It's kind of in between distributed memory. Distributed memory, basically everybody's in different address space. You have to map by sending a message. Here, you just say I have to flush and send it to the other guy. So some of the early machines, as well as some big machines, were no hardware cache coherence. Things like supercomputers were built in this way because it's very easy to build. And nice thing here is, if you know your applications well, and if you run good parallel large applications, and you're actually knowing what the communication patterns are, you can actually do it, and you don't have to pay the hardware overhead to have this nice hardware support in there. However, a lot of small scale machines, for example, most people's workstations and stuff is probably now two Pentium Quad machines and stuff like that, are shared memory. because if you are trying to do the starting thing, it's much easier to do shared memory, and also it's easier to build small shared memory machines. And we will talk about using a bus-based machine and also using large-scale directory-based machine in here. So bus-based machines, how do you do shared memory? So there's a protocol, what we call a Snoopy cache protocol. What that means is every time you modify a location somewhere, so of course you have that in your cache, you tell everybody in the world for using a bus saying, I modified that. And what that, and then if somebody else also has that memory location, that person says, oops, he modified it. He either invalidates it or get the modified copy. If you are using something new, you have to go and snoop, and you can ask everybody, say, wait a minute, does anybody have a copy of this? And some more complicated protocols have saying, I don't have any. I have a copy, but it's only read-only. So I'm just reading it. I'm not modifying it. Then multiple people can have the same copy because everybody is reading and it's okay. And then there's the next saying, okay, I'm actually trying to modify this thing, and then only I can have the copy. So some data you can go to multiple people as a read copy, and then when you're trying to write, everybody get invalidated, only the person who write has access to it. And there are a lot of complicated protocols how if you write it and then somebody else won't write it, how do you get to that person? And of course you have to keep it consistent with memory. So there's a lot of work in how to get these things all working, but that's the kind of basic idea. So directory-based machines are very different. In directory-based machines mainly, there's a notion of a home node. So everybody has local space, okay, in memory. You keep some part of your memory, and of course you have a cache also. So you have a notion that this memory belongs to you. And every time I want to do something with that memory, I have to ask you. I have to get your permission saying, I want that memory. Can you give it to me? And so if there are two things. That person has it directly. It will keep saying, okay, this memory is in me. I am the one who right now owns it, and I have the copy. Or it will say, I have given a copy that memory to this other guy to write, and here's that person's address or that machine's name. Or if multiple people have taken this copy and reading it. So when somebody asks me for a copy, assume you ask for to read this copy. And if I have given it to nobody to read, or if I have given other people to read this, I say, okay, here's the copy, go read, and I add, say, okay, that person is reading that, and I keep that in my directory. Or if somebody is writing that, I say, shoot, I can't give it to read because somebody is writing that. So I can do two things. I can tell that person saying, okay, you have to get it from the person who's writing. So go directly get it from there, and I will mark that now you own it as a read value. Or I can tell the person who writes saying, okay, look, you have to give up your write privilege. If you have modified, give me the data back. And that person goes back to either read or no privileges for that data. When I get that data, I'll send it back to this person and say, here, you can read. And the same thing if you ask for write permission. If anybody else has needed read permission, I have to tell everybody, okay, now you can't read it anymore. Go invalidate because somebody is about to write. Get the invalidate request coming back, and when it's done that, I say, okay, you can write that. So I kind of, everybody keeps part of the memory and then owns that in there. So because of that, you can really scale this thing. So if you look at a bus-based machine, so this is the kind of way it looks like. You have a cache in here, microprocessor, and central memory, and you have a bus in here. And a lot of small machines, including most people's desktops, basically fits in this category. And you have a Snoopy bus in here. So a little bit of bigger machine, something like a Sunfire, basically had a bunch of 4 processors in a board, 4 caches, and had an interconnect that actually has multiple buses going, so you can actually get a little bit of scalability, because here's the bottleneck. The bus becomes the bottleneck. Everybody has to go through the bus. And so you actually get multiple buses to get bottleneck, and it actually had some distributed memory going through a crossbar here. So this cache coherent protocol has to deal with that. And going to the other extreme, something like SGI Origin basically had in this machine, it had 2 processors and had a bunch of actually a little bit of processor and a lot of memory dealing with the directory. So you keep the data, and you have to keep all the directory information in there. In this, and then it goes. Then after that, it almost use a normal message pattern type network to communicate with that, and they use the Cray interconnect network, so you can have a very large machine built out of that. So now let's switch to Multicore processors. So if you look at the way we have been dealing with VLSI, every generation we are getting more and more transistors. So at the beginning, when you have enough transistors to deal with, people actually start dealing with bit level parallelism. So you can do 16 32-bit machines. You can do wider machines because you have enough transistors. Because at the beginning you have like 8-bit processors, 16-bit, 32-bit. And then at some point you said, I have still more transistors. I start doing instruction level parallelism in a die. So when you do bit level parallelism, in order to get 64-bit, you had to actually have multiple chips. So in this regime, in order to get parallelism, you need to have multiprocessors. So in good old days, you actually build a processor, things like a mini computer. Basically, you had one processor dealing with one bit slice, so either 4-bit slice, or so for dealing with that's the amount you could fit in a chip, and multi-chip made a single processor. Here, multi-chip made a multiprocessor. We are hitting a regime where a multi-chip, what it will be multiprocessor, now fits in one piece of silicon because we have more transistors. So we are going into a time where multi-core is basically multiple processors on a die, on a chip. So I showed this slide. We are getting there, and it's getting pretty fast. We had something like this, and suddenly we accelerate. We are having more and more cores on a die. So I categorize multicores also the way I categorized the previously. There are shared memory multicores, and here are some examples. Then there are shared network multicores, and cell process one, and at MIT we are building also a row processor. And there are another part what I call crippled or mini cores. So the reason in this graph you can have 512 is because it's not Pentium size thing sitting in there. You are putting very simple small cores and having huge amount of them. So for some class of application, that's also useful. So if you look at shared memory multicores, basically this is an evolution path for current processors. So if you look at it, what they did was they took their years worth of and billions of dollars worth of engineering building a single superscalar processor. Then they slapped few of them on the same die and say, hey, we got a multicore. And of course they were always doing shared memory or using at the network level. They said, okay, I'll put the shared memory bus also into the same die, and I got a multicore. So this is basically what all these things are all about. So this is kind of gluing these things together. It's the first generation. So you didn't build a core completely from scratch. You just kind of integrated what had in multiple chips into one chip, and basically got that. So to go a little bit beyond, I think you can do better. And so for example, people like this AMD multicore, basically you have CPUs in there and actually have full Snoopy control in there, and can have some other interface to that. So you can actually start building more and more, even the CPU thinking about that you are building a multicore, instead of saying, okay, I had this thing in my shelf, I'm going to plop it here and then kind of spare that. And you'll see, I think, a lot of interesting things happening, because now as they're connected closely in the same die, you can do more things than what you could do in a multiprocessor. So in the last lecture, I'll talk a little bit about what the future could be in this kind of regime. Oops. Come on. Okay. So one thing we had been doing at MIT for, now this project is ended, we started about 8 years ago, is to figure out, when you have all this silicon, how can you build a multicore if you start from scratch? So we built this row processor where we have 16 these small cores, identical ones in here. And the interesting thing is, what we said was, we have all this bandwidth. It's not just going from pins to memory. We have all this bandwidth sitting next to each other. So can we really take advantage of that to do a lot of communication? And also the other thing we said was, to build something like a bus, you need a lot of long wires, and it's very hard to build long wires. So in row processor is something like each chip, large amount of part is into this 8 32-bit buses. So you have huge amount of communication next to each other. And we don't have any kind of global memory because that requires right now either do a directory, which we didn't want to build, or have a bus, which will require long wires. So we did in a way that all wires, no wire is longer than one of the cores. So we can do short wires, but we came up with a lot of communication. So each of these, what we call tile those days, are very tightly coupled. So this is kind of a direction people perhaps might go, because now we have all this bandwidth in here, because and how to take advantage of that bandwidth. So this is a different way of looking at that, and in some sense the cell fits somewhere in this regime, because what cell did was, instead of it says, okay, I'm not building a bus, I'm actually building a ring network, I'm keeping distributed memory, and provide the cell a ring. I'm not going to go to cell because actually you had a full lecture last day for yesterday on this.
So can I ask you a question?
Okay.
Is there a conclusion that I should be reaching in that? I look at the multi-cores you could buy today are still by and large 2 and 4 processors. Those that people talk about more. The raw has 16 and the cell has 8. And the conclusion that I want to reach is that if you, as an engineering trade-off, if you throw away the shared memory, you can add processors. Is that a straightforward trade-off?
I don't think it's a shared memory. I mean, you can still have things like directory-based cache coherent things. I don't think what's missing right now is what people have done is just basically took parts in their shelves and kind of put it into the chip. If you look at it, if you put 2 chips next to each other on a board, there's a certain amount of communication bandwidth going here. And if you put those things into same die, there's about 5 orders of magnitude possibility to communicate. We haven't figured out how to take advantage of that. So in some sense, we can almost say, I want to copy the entire cache from this machine to another machine in a cycle. I don't know why, I don't think anyone would want to do that, but you can have that level of huge amount of communication. We are still kind of doing this evolutionary path in there saying, but I don't think we know what cool things we can do with that. There's a lot of opportunity in that in some sense.
You think if you're clever, you could have your cake and eat it too.
Yeah, because the interesting thing is, the way I would say is in good old days, parallelization sometimes was a scary prospect, because minute you distribute data, if you don't do it right, it's a lot slower than sequential execution, because your access time becomes so large and you're basically dead in water. In this kind of machine, you don't have to. There's so much bandwidth in here. Latency, but still latency would be better than going to the outside memory, and we don't know how to take advantage of that bandwidth yet. And my feeling is, as we go about trying to rebuild from scratch multi-core processors, we'll try to figure out different ways. So for example, people are coming up with much more rich semantics for speculation and stuff like that, that we can take advantage of that. So I think there's a lot of interesting hardware microprocessor and kind of programming research now, because I don't think anybody had anything in there saying, here's how you take advantage of this bandwidth. I think that will happen. The other extreme is these mini cores. So for example, this Pico chip has array of 322 processing elements. They have 16-bit RISC, so it's not even a 32-bit match. Piddly little things, 3-way issue and they had like 240 standard. This basically nothing more than just a multiply and add in there. 64 memory tiles, 4 control, and 14 some special purpose function accelerators. So this is kind of heading towards what people call heterogeneous systems, where what they say is, we have all these cores. Why do you make everything same? I can make something that's good doing in graphics, something that's good doing in networking, so I can kind of customize in these things. Because what we have in excess is silicon. We don't have power in excess. And so we can't in the future, you can't assume everything is working all the time, because that will still create too much heat. So you kind of say the best efficiencies for each type of computation, you have some few special purpose units. So you kind of say, okay, I'm going to do, if I'm doing graphics, okay, I fit to my graphics optimized course, I will do that, and then minute I want to do a little bit of arithmetic, I'll switch to that, and sometimes I am doing TCP, I'll switch to my TCP offload, stuff like that. Can you do some kind of mixed in there? The problem there is you need to understand what the mix is. So you need to have a good understanding what that mix is. Advantages, it will be a lot more memory efficient. So this is kind of going in that direction. And so in some sense, You have, if you want to communicate, you have the special communication elements. You have to go through that, and process can do some work, and there's some memory elements, so on and so forth. So that's one push. People are pushing more from embedded, very low power end.
This is starting to look more and more like an FPGA, you just said.
Yeah, I mean, it's a kind of a combination of because the thing about FPGAs, it's this darn 1-bit LUT that doesn't make sense to do any arithmetic. So this saying, okay, instead of 1 bit, I am doing 16 bits, because then I can have very efficiently build ALUs, because I don't have to build ALUs out of scratch. So I think that's interesting convergences happening, because what happened, I think, for a long time was things like architecture and programming languages and stuff like that kind of got stuck in a rut, because there was a very efficiently implemented. It's like doing research in airplanes, because things are so efficient, so complex. Here, Aeroastro can't build an airplane because it's so. There's it's a 9 billion thing job to build a good airplane in there, and it became like that. Universities could not build, because if you want to build a super scale, it's again a 9 billion type endeavor to do that. Thousands of people. It was very well customized. But now it's kind of hitting the end of the rope. So everybody's going back and say, geez, what's the new thing? And I think there's a lot of opportunity to kind of figure out if there's some radically different thing you can do. So this is what I have for my first lecture, or some conclusion, basically. I think for a lot of people who are programmers, there was a time that you never cared about what's under the hood. It just, you knew it was going to go fast, and in AI it will go faster. I think that's kind of coming to an end. And there's a lot of variations, choices in hardware, and I think software people should understand and know what they can choose in here. And many will have performance implications, and if you know these things, you will be able to get high performance software build easy. You can't do high performance software without knowing what it's running on. However, there's a note of caution. If you become too much attached to your hardware, we go back to the old days of assembly language programming. So you see, I got every performance out of now the cell says they have 7 SPEs. So in 2 years, they come with 16 SPEs, and what's going to happen? I mean, you think it's still working on 7 SPEs very well, but it might not work on 16 even with that. But of course, you really customize for cell today, and I guarantee you it will not run good with the Intel probably Quad Xeon processor, because you will be do something very different. And so there's this tension that's coming back again. How to do something that is general, portable, malleable, at the same time get good performance with hardware being exposed. I don't think there's an answer for that. And in this class, we are going to go one extreme. We are going to go low level and really understand the hardware and take advantage of that. But at some point, we have to probably come out of that and figure out how to be, again, high level. And I think these are open questions.
Do you have any thoughts, and this may be unanswerable, but how could cell really succeed, and other such, I mean, not cell only, but some of these other ones that are out there, like, given how hard they are to program and
So I have this talk that I'm giving at all the places. I said the third software crisis due to multicore menace. I mean, I termed it a menace because it will create this thing that people will have to change. Something has to change. Something has to give. I don't know who's going to give. Either people have to say, this is too complicated. I am happy with the current performance. I will leave for next 20 years at the today's level of performance. I doubt that will happen. Okay. The other end is saying, okay, geez, I'm going to learn parallel programming, and I will deal with locks and semaphores and all those things, and I'm going to jump in there. That's not going to happen either. So there has to be something in the middle. And the neat thing is, I don't think anybody knows what it is. And that's being in industry, it makes them go terrified, because they have no idea what's happening. But in university, it's a fun time. Okay, so we'll take about 5 minutes break and switch gears into concurrent programming.